The following is an original production of AZPM News.
For Arizona Public Media, I'm Tim Swindle, Professor Emeritus of Planetary Science at the University of Arizona, and this is Arizona Science. Joining me today is Ewan Douglas, an Associate Professor of Astronomy at the University of Arizona and the Principal Investigator for two instruments scheduled to fly aboard the privately funded Lazuli Space Telescope, scheduled for launch in 2029. Welcome, Ewan.
Thank you.
Ewan, could you tell us a little about the Lazuli telescope and what makes it unique?
So Lazuli is a 3-meter space telescope, a little bit larger than Hubble. And one of the unique things is that we're trying to get it off the ground really quickly using off-the-shelf parts. So putting together a very large telescope, but not really spending a lot of time on R&D, but just putting the pieces together to build the best instruments we can with the technology available today, build that and get it into space as quickly as possible.
And by building it quickly, the best equipment available at the time you select it is closer to state-of-the-art than it is with something like the Hubble, correct?
Yes. It won't have that long time delay between selection and launch if we can get it out the door quickly.
And how is this being funded?
It's privately funded philanthropically by the Eric and Wendy Schmidt Observatory System, which is part of Schmidt Sciences.
And is this the first privately funded space telescope?
As far as I'm aware, certainly on this scale.
What are the instruments that you are leading?
So the two instruments we're building at University of Arizona are a wide field camera, the wide field context camera, and an extrasolar coronagraph, which is so the wide field instrument will look at different colors over large swaths of the sky at once, and the extrasolar camera will look at a narrow slice of the sky and really precisely block out starlight so you can look for planets and asteroid belts around the star.
I understand you're using adaptive optics for part of this?
Yeah, for the coronagraph, we have deformable mirror, two actually, that can correct its shape to tens of picometers. So any changes in the telescope due to temperature drifts or manufacturing, we can correct that out over a small area of the sky.
The University of Arizona has been a leader in developing adaptive optics for ground-based telescopes to correct for the shimmering of the atmosphere. But this is the first I've heard of using adaptive optics in a space-based telescope.
It's nearly impossible to build a telescope that's accurate enough to block out starlight at the part in a billion level. We need to see solar system-like planets. The manufacturing requirements on the optics would just be impossible to polish in the lab. But we can make those optics at the nanometer levels and then use these deformable mirrors to correct them down to the picometer levels. This part in a billion is really hard to visualize. I usually tell people it's something like a few grains of flour in a 5-pound bag or a few stars in the Milky Way are these part in 10 billion or part in a billion measurements we're trying to make. So we have to block the starlight out that accurately.
And ultimately what you're trying to do is to see planets directly, which is, as you say, very, very difficult to do. How many planets have been directly imaged, and how many more could be with a system like this?
We expect there's probably planets around every star at this point. And what we don't know is how many planets are like our own or like our giant planets. Ground-based telescopes have detected a handful of planets, but they're all very young, and we're seeing them in their thermal emission as they cool down. And we haven't seen any planets directly and measured their colors the way we've observed our solar system planets. So we need technologies like the coronagraph on Lazuli to do that, and Lazuli's coronagraph should be capable of detecting a handful of these solar system type planets if we get lucky. And they're there, right? There's a randomness to where in the sky they are, which stars they're around. So we're going to look for those. And we'll also see, we know most stars have matter around them, circumstellar disks or asteroid belts. So we'll be looking for that too.
Is the idea that Lazuli will be up for decades taking data, or is this more of a demonstrator to build a bigger telescope that will be the real workhorse?
Not exactly either. It will be a quick demonstration of the technologies we have today for a few years, what science we can do. But I don't think there's a long-term, multi-decade plan. I think right now we have to show that we can build something this quickly, and then we'll see where we end up.
How did you become interested in adaptive optics and instruments and that sort of thing?
I've always been interested in astronomy and exoplanets. My path to exoplanet imaging was by way of interferometry, working at the LIGO Observatory, and then sort of combining those technologies with being interested in the solar system to see other solar systems with interferometry and high resolution imaging. Sort of evolved as I went through grad school.
And University of Arizona is a good place to be doing things like adaptive optics.
Arizona is an amazing place to be doing adaptive optics. One of the things that's enabling us to go really fast with Lazuli is we have so much really high quality open source software to control telescopes and particularly adaptive optic systems that we've been running for a long time on ground-based telescopes. So the adaptation to space of the technology part is fairly straightforward, and we're building on all of that work that's already been done by the AO groups at Arizona. Another thing that makes U of A particularly well-suited to projects like this is the infrastructure we have in place, especially recently the Applied Research Building coming online, which gives us very large clean rooms and test facilities, so we can build hardware and test it in the same building, and that will help us accelerate the pace of building these instruments. Also having the interdisciplinary combination of optics, planetary science, and astronomy departments working together has also made it much easier to build the collaboration that can build these instruments quickly. And the pioneering work, if you'll forgive the pun, of the pioneers missions like Aspera has also been blazing the trail for these sort of quick turnaround, lower cost projects for space science.
This is scheduled to launch in 2029, correct?
I don't think there is a particularly scheduled launch date, but definitely this decade is the goal.
Then what's next for you after this? This is kind of a short time scale for building an instrument and then moving on.
I want to keep building instruments, keep pushing towards directly imaging smaller and smaller planets. I'm also involved in the Habitable Worlds Observatory, which is NASA's 6 to 8 meter class observatory that would be launching next decade or the decade after that, but would be looking for signs of life on exoplanets. So not only would it be detecting an Earth-like planet, that part in 10 billion measurement, but also doing spectroscopy and looking for signs of life.
Well, thanks for talking with us, Ewan. It'll be fascinating to see how the Lazuli Telescope develops and these other projects as well. This is Tim Swindle, and you have been listening to Arizona Science. We have been talking with Ewan Douglas, who is leading the development of 2 instruments aboard the privately funded Lazuli Space Telescope. You can hear more of this conversation and others on our Arizona Science segments by going to the AZPM podcast at azpm.org.
This has been an original production of AZPM News.